All right, in this work example, we're looking at electron-positron matter-antimatter annihilation. So when particles meet their antiparticle component, they're going to annihilate to make pure energy. And this question is about an electron meeting its antiparticle, known as the positron. We know that an electron and a positron are antiparticles because they have the same mass, as is explained here, but they have opposite charges. It reads, a positron interacts with an electron. The electron and the positron may be considered to be at rest. The outcome of this interaction is that the electron and the positron become two gamma ray photons, each having the same energy. Calculate for one of the gamma ray photons the photon energy in joules. So in order to solve this, we're going to use Einstein's famous equation E equals mc squared. We can solve for the energy by considering the mass of an electron, which is known as 9.11 by 10 to the negative 31 kilograms, and multiplying it by the speed of light, which is approximately 3 by 10 to the 8 meters per second. Don't forget to square that. Working through all of that in the calculator, we would get 9.11 by 10 raised to the negative 31 is there, times 3 by 10 to the 8 squared equals which will turn it. And so we get for an answer there 8.2 by 10 to the negative 14 joules. As a bonus calculation, let's convert that into electron volts. So divide by 1.6 by 10 to the negative 19 joules per electron volt if you're converting joules into electron volts. With this value still in my calculator, I can divide by and realize that that's a lot of electron volts. So you get, now they want the answer in joules, so we report that answer, but just for sort of our own curiosity, 5.12 by 10 to the 5 electron volts. In astronomy, we've been using sort of the energy evolution of the universe to consider when the universe was more energetic, when would these reactions have been occurring just after the Big Bang? The question goes on to ask for the momentum of one of the photons. And in order to solve this, we're going to use the idea that the wavelength of something is equal to Planck's constant divided by momentum. So let's make momentum the subject here. Divide by this. So we realize that momentum is equal to Planck's constant divided by the wavelength. You may recall the energy from a moment ago is 8.2 by 10 to the negative 14 joules. In order to get the wavelength, we will use this equation to get the frequency and this equation to get the wavelength. So the energy we know, so frequency we can get by dividing each side of this by h. And so frequency is energy over Planck's constant, the energy we previously calculated. Planck's constant is 6.626 by 10 to the negative 34 joule seconds. So what's that going to give us? My other calculation. All right, so I already got my 8.2 by 10 to the negative 14 there. I'll divide that by Planck's constant, 6.626 times 10 to the negative 34. And that gives a frequency of 1.23 by 10 to the 20. Hertz are the units of frequency. You can see that reciprocal seconds are the same thing as hertz. Little bonus physics knowledge for you there. And then we can solve for the wavelength using this equation as, let's see, wavelength would just be c over f. And so we'll plug in the speed of light, 3 × 10⁸ meters per second, divided by this many reciprocal seconds. Reciprocal seconds will cancel. We'll have meters of wavelength. We can then plug back into this equation for momentum. All right, so we've got, figure that all out. Three by 10⁸ divided by 1.23 by 10⁻²⁰. So that gives us a wavelength of 2.4 by 10⁻⁻12 meters. Trillionth of a meter, a picometer is the range that we're sort of in here. Slide that one over. And now we're ready to calculate the final momentum, the answer to the question. Planck's constant again. Divided by the wavelength, which we just calculated, 2.4 by 10⁻⁻12 meters. And then we will get Newton seconds of momentum there. If we were to consider that a joule is a Newton meter, then the meters would cancel and we just have Newton seconds, right? So a joule is a Newton meter. All right, so the last calculation here is, clean this up a bit over here. Planck's constant again, 6.626 by 10⁻⁻34. Divided by, your grouping symbols there when you're dividing by values in scientific notation, 2.4 by 10⁻⁻12 for that much momentum in that gamma ray photon, 2.8 by 10⁻⁻22. The very last part of this question asks, state and explain the direction relative to each other in which the gamma ray photons are emitted. So here we've got the law of conservation of momentum. The initial momentum has to equal the final momentum. Because it says that the particles are at rest initially, the initial momentum is 0. And so if the final momentum was, non-zero, that's because the photon is flying along in some direction this way. So the other photon must be going in the opposite direction. So that way the vector nature of velocity is what cancels out sort of the momentum in this direction with the momentum in that direction. So they move in opposite directions in order to conserve momentum. This has been another worked example with Dr. Schleich, and we'll see you next time.